Welcome to Lecture 19. Today we're going to be discussing blowdown and the exhaust valves opening and the sequence of valves. So let's dive right into blowdown. Blowdown occurs between when the exhaust valve opens and bottom dead center. So blowdown is where the pressure built up in the chamber drives a large portion of the mass in the cylinder out of the cylinder before the piston has to do any work of pushing that mass out. So it's just the built up pressure that expels itself. Typically we design the engines so that blowdown finishes before or at bottom dead center because we want to minimize the pumping work of the piston pushing that mass out. So if we can get the pressure down to a reasonable level before bottom dead center, it helps minimize that pumping work. So that's why it's not an absolute requirement that blowdown finishes before bottom dead center, but it is a design consideration that we generally design the valve open, the time at which the valve opens, so that the pressure dip driven part of blowdown has finished before bottom dead center. Now, because at the end of the power stroke the pressure in the cylinder is 400 to 500 kilopascals and the exhaust pressure is typically atmospheric, we're definitely going to have choked flow at the moment that exhaust valve opens. Now, how long it remains choked is to be determined, but typically the inlet flow, unless it's a supercharged or turbocharged engine, is the unchoked flow equation. Blowdown will be typically using the choked flow equation, and then the pumping part of the exhaust will be unchoked. Yes, so after blowdown the exhaust stroke pushes the remaining mass out of the cylinder, and that's generally unchoked. And then we typically keep the valve, the exhaust valve, open a little bit after top dead center to try and push out as much of the previous charge of air and fuel out. So if the inlet valve opens a little before top dead center, some of that air rushing in will help push the final bit of air out of the engine, particularly with a supercharger or turbocharger. And so that period between when the inlet valve opens and the exhaust valve closes is known as the valve overlap, and that's an important design consideration in all engines. So let's talk about the sequence of engines events when it comes to the valve. So the first thing that happens in each cycle is that the inlet valve opens, and that'll typically happen 10 to 15 degrees before top dead center. If we open it too early, we get backflow from the exhaust back into the cylinder, and it dilutes the fresh charge of air. If we open it too late, we reduce our volumetric efficiency, which hurts the efficiency of the engine. So the next event that happens is the exhaust valve closes. If you close the exhaust valve too early, you won't be able to push all the previous charge out of the engine. If you close it too late, you're pushing out some of the fresh charge of the next cycle. So you would reduce your compression ratio if you close the exhaust valve too late. And so we have a basic formula for the valve overlap, which is the angle at which the exhaust valve closes in terms of after dead center minus the point at which the inlet valve opens, which would be, here negative 10 to negative 15 degrees after top dead center. And so that combined would give us a typical valve overlap somewhere between 15 and 30 degrees. Now the next event, sort of at the top of the cycle, we've opened the inlet valve for the next charge, we've closed the exhaust valve on the previous charge. Now during that downward stroke, we're taking in the full next charge of air. We hit bottom dead center, and then a little bit after bottom dead center is where we close the intake valve. And remember, we leave that intake valve open a little longer than bottom dead center because of the ram effect of the air coming in. So you're using that inertia of the air to come in to increase the volumetric efficiency. Then after that you have your compression stroke, followed by ignition and combustion somewhere near top dead center of the power cycle. And then typically combustion is ending somewhere 40 to 60 degrees after top dead center. After the end of combustion you have a expansion stroke, and then partway through that expansion stroke you're going to open the exhaust valve because you want blowdown to try and finish before bottom dead center. So you want to leave enough time here, 20 to 60 degrees of crank angle rotation, to get that mass out of the cylinder before you have to push it out. So there's a few ways to sort of imagine this sequence. You can work sort of in radial coordinates where the cycle starts here at the exhaust valve opening where you start to bring in the next charge of air, and then partway through that sequence the exhaust valve closes from the previous cycle, and then you're taking in your fresh charge of air all the way until your inlet valve closes sometime after bottom dead center, and then you compress, ignite, combust, and then expand your gases down to the point where the exhaust valve opens. Then you have your blowdown to bottom dead center, and then you're pushing the mass out of the cylinder during the exhaust phase, and at some point your inlet valve opens for the next cycle, and then you close the exhaust valve for this cycle. So that's your four-stroke cycle, 2 revolutions per cycle, laid out on a sort of linear timeline and plotted against pressure. You can see that when the inlet valve opens you start drawing a vacuum in the cylinder, so the pressure is very low during the intake stroke, and then you close the inlet valve and begin the compression stroke. Pressure goes up, combustion raises the pressure, and then you begin expanding and the pressure drops, and then at some point you open the exhaust valve and you try and have blowdown completed before bottom dead center, and then you've got a little bit of pumping work as you push that exhaust out. So a couple examples of just the timing of these valve events. How would you calculate the valve overlap? So here's the first problem, is that both the inlet and exhaust valve are open for 230 degrees of crank rotation. The exhaust valve opens 25 degrees before bottom dead center to ensure blowdown is complete, and at 2000 RPM the inlet valve closes 20 degrees after bottom dead center. So this is sort of telling us exhaust valve opening and inlet valve closing, which are both somewhere in the vicinity at bottom dead center, and we need to use this 230 degrees of crank rotation to figure out the opposite part of that event, because that's what determines the overlap. So if I assume the overlap is when the exhaust valve closes, since I know the exhaust valve opens 25 degrees before bottom dead center and it takes 230, or it's open for 230 degrees, that's going to become 25 degrees after top dead center when you put those two things together. Likewise, if the inlet valve closes 20 degrees after bottom dead center and I back up 230 degrees to when it opens, I find that it opens 30 degrees before top dead center, and then I'm going to convert this 30 degrees before top dead center to a negative 30 degrees after top dead center, so that I'm subtracting with the same units, and that'll give me 55 degrees of valve overlap. Now, a slight twist on this question is what happens with variable valve timing. So in this imaginary engine, variable valve timing is employed to ensure that blowdown is completed before bottom dead center. So when the engine speed doubles, let's imagine the exhaust valve opens twice as early as original. It needs the same amount of time for blowdown to occur. So the crank angle when the engine's spinning twice as fast, the crank angle would have to be 50 degrees before bottom dead center. So now let's refine the valve overlap under those conditions. The new exhaust valve opening would be 50 degrees before bottom dead center to make sure we have the same amount of time for blowdown to occur. And if it opens 25 degrees earlier, that means it's going to close 25 degrees earlier, so it'll now be at 0 degrees after top dead center. And the inlet valve opening stays at the same time, so I now have 30 degrees of valve overlap. Those sorts of problems should be fairly straightforward. It's just looking at things on this radial coordinate system or this time axis and just making sure you can find out how much the valve overlap is from here to here. Okay, let's recap the valve flow we did for inlet valves, and now we'll be working more with the exhaust valves, so it'll be a bit different conditions. Before we define this effective area through which the air will flow, now we're talking about flow in the outward direction, but the equation is still the same. The cross-sectional area is some discharge coefficient times pi times the diameter of the valve times the lift. Now we had an equation for flow through a non-choked valve, and that'll apply mostly during the exhaust stroke. And then if the valve pressure or the stagnation pressure relative to the valve pressure is greater than this function of gamma, typically about 1.86 for air, then it's choked flow, and we'll use the choked flow equation, which is a little bit low on this slide, but that's what it is. So let's work through an example of how we would apply this to blowdown. So let's imagine a 2.8 liter 4-cylinder 4-stroke spark ignition engine operating at 3000 RPM with a peak temperature and pressure of 2600 Kelvin and 10,000 kilopascals at 20 degrees after top dead center. So again, note I'm not giving the pressure and temperature before compression. This is at the end of combustion at the peak pressure and temperature. The compression ratio is 8, the crank offset is 4 centimeters, rod length is 20 centimeters, exhaust valve diameter is 3 centimeters with a 6 millimeter lift, and a discharge coefficient of 0.5, so we can find that cross-sectional area. Let's imagine that the valve lift takes 4 degrees of crank angle, so we can't instantaneously lift that valve. The cam has to be somewhat rounded just to be smooth as it's rotating at 3000 RPM. So it takes some time to push that valve open. And our goal here is to find the minimum angle before bottom dead center for the exhaust valve to open so that the flow becomes unchoked at or before bottom dead center. Now this is a very complex equation, and it's actually can't be solved explicitly without iterating in a function. So what I want to walk through is sort of what would go into solving this, and then show you the results of programming a solution to this problem. And then we'll go through a simplified estimate where we make some additional assumptions that allow us to estimate this crank angle where exhaust valve would need to be open. So the best way that I've found to solve these sorts of problems is throw it at a computer, take small enough steps that everything becomes linear. So the equations we would need is the volume as a function of theta, the mass change, so the mass in the cylinder would be the mass before the exhaust valve opens minus the integral of the mass leaving the cylinder. The density would then be this mass that remains in the cylinder divided by the changing volume of the cylinder. And then I want to change this to actually, So pressure follows the isotropic relation. Temperature, though, we're going to change this to the P of theta over P of theta EVO to the gamma minus 1 over gamma. And I've updated that in the slides I posted online. The reason for that is once the exhaust valve opens, the control volume is no longer just the cylinder, because some of the mass that is expanding has now expanded out into the exhaust system. So it's better to use the change in pressure to calculate this isentropic change in temperature. The cross-sectional area equation remains the same. What I've introduced here is the fact that the lift takes 4 degrees to open and then stays open. So the lift on that valve is a function of theta. It increases linearly from 0 to 4 degrees and then stays open. The speed of sound is going to change slightly as the temperature of the gases in the cylinder change. And then finally, we're going to assume that it's choked during this entire blowdown phase. So we're going to use the choked mass flow equation. We have the density, which changes as a function of crank angle, the cross-sectional area, which changes as a function of crank angle because of the lift on the valve, the speed of sound, which changes as a function of crank angle because of temperature, and then this post-multiplier function of gamma. So if I put those into a loop and solve for very small steps in crank angle, what I can get are results that look like this. You can see this first chart is showing the mass flow. So for the 4 degrees that the valve takes to open, you have an increase in mass flow. And then as the density of the mass remaining in the cylinder drops, you get a reduction of mass flow. So that's the main driver here, is this density of the upstream stagnation flow tends to change. Speed of sound changes a little bit. After this valve is open, the cross-sectional area doesn't change at all. So what's driving the change in mass flow is the fact that the upstream density is changing. The volume of the cylinder is remaining nearly constant because we're pretty close to bottom dead center, and there's mass leaving. So as the mass leaves, the density goes down and the mass leaves slower and slower. Now the second chart here is showing the mass that remains in the cylinder. You see there's some initial acceleration of the drop in mass, and that's because this mass flow is increasing, and then it starts to slowly level off as it exhausts. Pressure follows a similar trend to the mass remaining in the cylinder. It drops off pretty fast, and then I've set this up so that at bottom dead center it reaches 186 kilopascal, so it's no longer going to be choked at bottom dead center. And I found that 16 degrees of crank angle rotation was enough to ensure that blowdown, the choked phase of blowdown, finishes before bottom dead center. So let's walk through a way to estimate that 16 degrees. So we're going to make some additional assumptions. We're going to assume that the flow remains choked from exhaust valve opening to bottom dead center. We're going to assume that the volume at the point that the exhaust valve opens is 90% of the volume at bottom dead center. So we're not so close to bottom dead center that we assume constant volume, but nearly constant volume. We're also going to assume that the gas cylinder temperature is constant during blowdown so that that speed of sound can remain fixed. So the first thing we'll do is we'll find the volume at the peak temperature and pressure conditions, so we know that the mass, we can find the mass that was in the cylinder originally. Then we'll find the volume, temperature, and pressure at the point the exhaust valve opens. And we can do that from this volume ratio. And then we'll find the volume at bottom dead center and compute the mass after blowdown. And then the difference of the original mass and this mass after blowdown will tell us sort of the mass that needs to be removed. And then we can find the choked mass flow rate, or speed of sound. Then we find the average mass flow rate, assuming an average density between these two. And then we'll find how long at that flow rate blowdown would take. And then we'll convert that to a crank angle. So, step one. What is the volume at 20 degrees? We were given the rod length and the crank offset, so this is just substituting in. I need to find the clearance volume, so I can use the displacement and the compression ratio to find that. So the displacement is in each cylinder is 7/10 of a liter. The clearance volume is 1/10 of a liter. And the volume at 20 degrees is 0.125 liters. So with all of that, I can find that the mass in the cylinder before we open the exhaust valve is 1.675 times 10 to the negative 3 kilograms. So then the volume when the exhaust valve opens is 90% of the volume at bottom dead center. So I can use that volume in the isentropic relations to find out how much the temperature and pressure have dropped during the purely expansion phase. So the temperature has dropped from 2600 Kelvin to 1400 Kelvin. And likewise the pressure has dropped from 10,000 kPa to 940. This is definitely going to give us a pressure ratio much greater than 1.86, so we're definitely choked. So now I need to find the mass after blowdown, and so I'm assuming that it's just become unchoked, so the pressure at bottom dead center is 186 kilopascals. I use the volume, and I'm going to make that constant temperature assumption, and that'll tell me the mass in the cylinder after blowdown. Now the speed of sound we'll calculate at that exhaust valve opening temperature, and we'll hold that constant. The cross-sectional area, we're going to neglect that lift as a function of theta and assume that the valve opens instantaneously. So that gives us a cross-sectional area during blowdown. And then we can find the average density during the blowdown event. So I'm going to take the mass in the cylinder before, this should be the volume at EVO. The mass in the cylinder divided by the volume when the exhaust valve opens. So that'll give me the density at the exhaust valve opening plus the density after blowdown. And the average of those two densities is 6.7 kilograms per second. Sorry, it's not a, that should be kilograms per meter cubed. Apologies. I can use that average density into my choked flow equation, assuming a constant cross-sectional area, constant speed of sound, and I get an average mass flow rate of 1.084 kilograms per second. Now, I know the total mass I need to remove from the cylinder is 1.3 times 10 to the negative 3 kilograms. So using this flow rate and that total mass, I can find the time, which is about 1.2 milliseconds for blowdown to occur. And then using the engine speed of 3000 RPM, I can convert that time to a crank angle, and I'll get 21.7 degrees. So close, but not terribly close to the 16 degrees that we calculated with the more detailed function. So the last thing I want to touch on today is expansion cooling, and this is just reiterating that during blowdown, what we want to use is the isentropic relation between temperature and pressure rather than between temperature and volume, because the volume is no longer confined to the cylinder. So an example of that would be, what is the temperature of the exhaust from the previous example? And we knew that the temperature when the valve opened was 1400 degrees, and then as it exhausts into atmospheric pressure, we can calculate the temperature, and I don't think I have the answer on this one. So yes, we'll just plug this exhaust pressure, I think it was like 960 kPa, and we would calculate the exhaust temperature from that. With that, I'll conclude and see everyone in class.